Hello all, welcome to the deep learning series. So in this video, we will see about how to train the deep learning models. So these are going to be the key takeaways. So we'll understand what's a loss function, so how to train a neural network, and what is backpropagation, optimization, gradient descent, and regularization. So we understood from the last video so that what is a neural network and how it will look like. So we see a single layer neural network, and we can also have a multi-layered neural network. So the difference is that like you have a single hidden layer. So you have um, a bunch of you can have n number of hidden layers as you want. So to perform your task. So in between the input layer and the output layer. So this is what we understood from the last video. But what we now understand or should understand is that like how to train the neural network. In the last video, what we understood was we give an input, we give the features, we give the weights of them, and we predict the output. But not always the predicted output is close to the actual one. So this is the predicted output. So y hat. So let's say the actual output is supposed to be 1. Your predicted output can be 0.1, which is far from the actual output. But we cannot stop or get satisfied with this network. This network has to be built better. So what we can do is that we can only align the weights. Okay, so now these are the inputs given, and this is what is the predicted output, but the actual output. So because this is supervised, so we would have had the labels of the data with us. So we know the actual output, and that is 1, and whereas the predicted output is 0.1. So we need to know the loss that we faced with this network. So this is the actual output, and this is what is the predicted. So we gave the input and the weights, right? So that and we gave the activation function. So this is the function. So that is the predicted output, and we have the actual. So this is the loss that was thrown by the neural network. Okay, there are so many laws we can use to compute the loss thrown by the network. So the one such loss is cross entropy loss, whose value is always between 0 and 1. So here j of w is the cost function. So when you see this 1 by n, so this n represents the number of inputs that we took for training. So we are taking the average. So this gives a single value. The loss is going to be a single value that is thrown by the model. So which is averaged out from the entire data. So what we see here, though this equation looks very clumsy, but when you look closer, what we are actually doing is that we are taking the average. N is the number of inputs. We are just iterating from 1 to n. That is, we are doing it for all the inputs. We are scanning all the inputs, and we are understanding the what is actual. This is the actual y, and this is the predicted. So we are calculating the loss. So for all the inputs that we had in our training data set, so we are calculating this loss. That's what. So we can also have for regression models, we can have the other loss function, that is mean squared error loss, whose equation is slightly different from that of the cross entropy loss. So what we actually what we actually need to do is that we need to optimize this loss. So once we face a loss, we need to optimize it. So how do we optimize it? The only one control we have with us is W. So W is a set of weights that we have for our network. So we need to find a W star, a new set of weights for our model in such a way that this is a loss. This entire thing is a loss. So in such a way that our loss is minimum. So we need to find such a W so that our loss j of W is the loss the cost that is thrown by the network. So that is finding the least value. So that's the optimization. So our goal is to find a set of weights for our neural network, and so that the loss is it's very less. Okay, so to go calculate the weight and to optimize the network weights, we have gradient descent algorithm. So we'll look at that. So here we have a graph that is plotted between the cost thrown by the weights, that is the loss, and the two weights. So there can be in reality there will be n number of the huge number of weight matrix we will have. For simplicity, we are drawing between two weights and its cost thrown. Okay, so what we actually aim for is the lowest, the least cost thrown by the model. So for the respective value of weights, so we need to check for such a kind of weight, that weight numbers, weight values, which gives us the least cost. So this is our desire. So, but right now, when we did the first forward propagation pass, we might be here. So how to reach here? So that's what this gradient descent algorithm teaches us. So what this gradient descent algorithm does, that is that. So initially, we are here. It's like we are on top of the mountain, and we need to climb down the hill. So our aim is to be here. So we need to climb down the hill, but we need to climb down in the optimum way. So what we do, we take tiny steps in the direction in such a way that it is the optimum path. So that's actually gradient descent algorithm. This we'll initially, what we do, we randomly take a guess. We close our eyes and we will guess a value that might be bad. That's okay. Then what we do is that we compute the gradient. So this step that we take is the gradient, right? So what we do, we take the partial derivative of that weight with respect to this cost function, and we will update the weight. How do we update the weight? We multiply that derivative into learning rate. We'll talk about the learning rate shortly. So it's just a value. As of now, we can understand that. So multiplied by the learning rate, and we will, this is the earlier weight, so the old weight. So we'll just subtract that, and we will update this weight. And now we will return a matrix of weights for our model. So now we have updated the weights. This is the new weight, and this is the old weight, and we took the partial derivative, and we'll return the weights. And then what we will do, we will loop until convergence, right? Like then we will just do it again and again and again. So we will climb down the hill till we reach the optimum global, or the local optimum value of the cost. So that's what gradient descent is about. So we have not seen about learning rate so far. We'll deal it shortly. So the goal is that to find the set of weights for the model, update the weights of the model iteratively till we get the optimum weights. So by just checking with the loss function that is incurred by the weights, we do this by using the gradient descent algorithm. Okay, so in the gradient descent algorithm, this stochastic gradient descent is similar to the gradient descent algorithm. So only it differs by the fact that, like, it does not do it for all the training data. So if we look at the gradient descent, every time it was doing for the entire training set. So in reality, the training set is going to be large, and the features are going to be large, and every time um, it's going to be computationally costly. So what we can do is that every time we can pick up a set of data points. We need not consider all the data points every time. So we can do it for B set of data, or we can do it for randomly. We can pick up a single data, and we can also do that. So that is also possible. So that is what a stochastic gradient descent, and then we can do the same. So this can be much faster than the gradient descent. Yeah. So this back propagation is nothing but, so we started with the forward propagation. We had some weights initially, and what back propagation says is that you have the input, you had the weights, and this is a hidden layer, so the activation function, and you reach the output and you calculate the loss, right? So then we travel in the reverse direction, so we calculate the partial derivative of this weight. So this weight with respect to so when you look at this derivative, it has many other derivatives internally. So because this weight is associated with um, the the predicted value y, and this predicted value is in turn dependent on the z1 output emitted by the activation layer in the middle, and this in turn is dependent on the w1 that was emitted by the input layer. So all these are multiplied in chain, and this is actually calculated. So using this and by using the gradient descent algorithm, we just travel backwards for each and every layer. We keep doing this. So this is for this. Um, we update the weights of each and every layer, and then we travel forward. We do a forward propagation and see like how much is the loss, and then we just go forward and backward until we are satisfied with our performance of the network. So like how much set of outputs are matching with the actual output. Okay, so now is the time to study about, know about the learning rate. So learning rate, here is the learning rate, so which we used to update the weights. So while we were on top of the hill, so we were taking some tiny steps, and we are reaching down the hill. So this learning rate tells us how faster or slower we can climb down. So that's what it. So if the values are very large, what happens is that we take steep steps. So our let's say, yeah, the star tells us this is the ideal point where we are supposed to find the weights, right? Like because we are randomly, let's say we are here, we are randomly taking some steps. If the value of learning rate is large, then what happens is that you take steep steps, and you might even miss this point. You may deviate and go. So that is what happens like when we take large steps. But when we take tiny, very, very tiny steps also, we might stuck in the local minima. So this is the local minima. So, but this is the global minima, which is the desired point we are supposed to reach. So it may not be too low, or it may not be too high. So it comes with trial and error method. So we can try which learning rate actually suits our model. So that's how we fix the learning rate. So learning rate basically tells us like how slower or faster we are climbing down the hill and reaching our optimum point. Yeah. So right now what we have done is that like we have updated the weights of the model using backpropagation. But even after doing so, what can happen to the model is that like either the model is underfit, or it is correctly fit, or it is overfit. So this always happens. The underfitting is nothing but like when we don't have enough number of, like, no matter how much perfectly you do the backpropagation also, if the features, the data itself is not sufficient, or the features are not sufficient, so then the model is unfit. It is not able to actually perform well. So how do we actually do this is that like you have the input data, so you split the input data into training data and test data. So even this training data is divided into validation set or the dev set. So you have validation set, and so this validation set will mimic as though it is a test set. So when we perform, so while doing the training itself, we understand like how well the model is performing even before introducing to the test set of data. So we can understand that like if the model is underfitting, so then there's something to be done with the input side, or and if it is ideal fit, it's fine. So overfitting happens if there's large number of features, it's then the model may not generalize. So when it is actually put on to the introduced to the test data it has never seen, it might not do well because it is overfitted with too much of features. Then it may not generalize towards the unseen test data. It might see later. Okay, so certain things can be done towards this underfitting and overfitting problem. So we have one solution, that is dropout. So dropout is nothing but we had, so these are actually faded out neurons. So there are actually neurons here, but while training, what we can do is that, so we can drop out certain neurons and we can do the training. So we can set their activation function value to be 0 and we can do the training. So let's and see like what is the actual loss that is thrown by the network. So if it is actually performing better or so. So maybe in first iteration, we can select few percentage of neurons, and in the second iteration, we can select some other percentage of neurons and see, choose different parts of the network and see like which is actually working out for us. So that is actually a dropout strategy. This we call it as regularizations. Regularization strategies usually usually alleviates the overfitting or the underfitting problem. And early stopping. So we were having this training and this testing set is actually validation set of the dev set. So what we can do is that like we need not overtrain. So this green graph is actually representing the training, and this is the validation set. So this graph is between loss and the training iteration. So how many training iteration we are actually doing? So here we can actually stop. So after this, like when the training is done, so the training data is actually performing well, but the validation set is not actually performing. So the loss is actually increasing. So that means like the data is not going to the model is not going to generalize later. So we can stop at this point. So that can prevent the model overfit. So if we do the training, maybe training data can perform well. You can get high performance for your training data, but not for your test data later. So that is early stopping. So this is about um, um, regularization strategies that can be adopted for preventing early overfitting and underfitting problems. So far, what we have seen till now in this video is that like how to train a neural network using backpropagation strategy. So in that we understood like how to calculate a loss and how to optimize the loss using gradient descent method. And we also learned about like what is regularization and how it can be implemented. Thank you.